All right. Sorry that today I'm a little low energy. I'm feeling a little bit. All right. So today we're going to talk about asymptotic freedom, and this is we're going to compute the beta function of Yang-Mills and argue that in non-abelian gauge theory, you could easily arrange for setups where beta functions are positive. And we'll see that the one loop beta function that we compute here's a like take-home lesson. The beta function that we compute at the end of the day will be completely fixed by the representation theory, right? Which is the gauge group, its representation. For example, if it's adjoint, it will be just things that come from the adjoint representation, in particular C2 of G, which for SUN was N. And then the number of fermions that run in the loop and the representation of the fermions. I think in the last lecture, I went over that way too fast, right? But I'll slow down when I do the repeat today. And that's all that goes to the one loop path integral, one loop beta function. I will do the effective in the at the end of this lecture. We're going to derive the beta function as one loop using effective actions, and then when we do it using effective action, it becomes very obvious why it's just fixed by kinematics. Does anyone actually have any idea why? The one loop effective action. What did it look like? The structure of one loop effective action. We just log a bunch of determinants. And where does the log of the determinant come from? Determinant of what operator? It's the thing that's second order, right? So you have two fields and the thing that sits in the middle, right? Which means that at one loop, for the calculation of effective action, then non-Gaussian terms won't matter, right? And the Gaussian term is completely fixed by representation theory. And it's completely fixed by representation theory and the number of fermions and all, right? So the one loop answer has that nature. All right. So, but the punchline, I want you guys to really, I think it's one of the most important calculations or answers that we found in quantum field theory, the beta function of Yang-Mills or non-abelian gauge theory. So it should become very intuitive. So we're going to spend quite a bit of time talking about it. As I review lecture 13, if there are any questions, please ask. All right, so a disclaimer, in version 2 of this course, when I teach probably next year, I will make sure that I stick to one gauge all throughout, but I will start with RC gauge, but halfway through, in some calculation, I'll fix C equal 1, right? That's just like, which is the Feynman gauge, All right. So if there are any questions, please ask. Here is the Faddeev-Popov path integral. Whoops. Here's the Faddeev-Popov path integral for the non-abelian gauge theory. There is the path integral over the ghost, the fermions, the gauge field. And then there's the Yang-Mills action plus matter, Yang-Mills plus matter, ghost gauge fixing, and then the ghost action, right? So the ghost action, well, okay, here it is. So Yang-Mills plus matter, gauge fixing, arc C gauge, yes. And then the ghost term. Good. All right. So we're gonna do integration by parts to write down the ghost term in terms of like a canonical term, just a kinetic term, plus this term, which is a vertex, right? So this is when we calculate the propagator for the ghost, this is what it was, right? It's massless right? So the propagator was I over Q squared plus I epsilon. And here's the vertex for ghost, anti-ghost, and gauge boson, which has a derivative in it. Why? Because gauge boson has a mu index, and the ghost is scalar. Good? All right, so the Feynman rules. Here's a propagator for the gauge boson and RCC gauge. It's a good old RCC gauge answer for QED, and then delta AB in the middle, multiplied, right? There is a fermion, which is a good old fermion answer. The ghost, as we just said, is diagonal in gauge indices, and it's just 1 over k squared here in this notation. Then there is a ghost gauge boson interaction, which looks like this, right? Of course, it has to be proportional to FABC because it has to vanish in the abelian case. The ghosts have to decouple from everything in a abelian case, right? So they have to go away. When I write here FABC, you already know that I'm in adjoint, right? Now, this is the adjoint representation for the gauge field, right? But here's a vertex for the fermion with the gauge boson, and this is the representation of the fermion, which could be in the fundamental or the anti-fundamental, right? So this is the part that I did not quite elaborate much on last time. I just went over the fermion pretty fast. So we're dealing with SUN. In SUN, in Yang-Mills plus matter, the gauge field, we're gonna be picking it to be in the adjoint. So we have T of G, G is the adjoint representation, C2 of G is N for SUN. But the fermions are in fundamental or anti-fundamental, right? T of fundamental, we usually write this way, N bar is half, and C2 of N is N squared minus 1 over 2N. So to distinguish between the two, I often put C of R here and C of G. Well, sorry, R and G. R is to refer to the fermion representation, and G to refer to the adjoint representation. I spent a lot of time in the last lecture talking about the because so in these Feynman rules I've written, I've already used the fact that the gauge boson is in the adjoint, right? So all the generator in the adjoint representations, I've plugged them in. What are they? FABCs. Right, so every time you see FABC, that was the generator, that was a Lie algebra generator for the adjoint representation, right? So the only thing that's left is just, when I write TA, what I mean is the representation of the fermions. Is that good? All right, so I have in non-abelian gauge theory, the gauge boson is self-interacting, so there is 3-point and 4-point function. 3-point is G FABC, and this is G squared F, 2 copies of it. Good. All right. We went over the BRC symmetry. The idea was to introduce a new commuting scalar field B of A, which was, and then consider this action. The goal, as we just discussed, was that as you integrate over this term, you're gonna get the Fedya-Popov-Lagrangian by completing the square. Actually, is this upstairs or downstairs? Oh, we'll check that. There might be a typo here. But the goal of this B of A was just completing the square, performing the path integral over B of A by completing the square will just give you the gauge fixing. This was analogous to what we did. So, yeah, okay, I should know over explain. Okay. All right, so this is the Lagrangian we start with. Then we said we can write down a symmetry, symmetry, transformation under which this Lagrangian is invariant, right? And this was basically the structure of this transformation looked like a gauge transformation, which was proportional to the Gauss field. Now, because the Gauss field is anti-commuting, then I'll have to put an anti-commuting variable as a coefficient that we called epsilon. So here's the variation. Of course, the first two terms are invariant because it transforms like it because they're just gauge invariant, right? The third term, it doesn't transform under this symmetry, quote unquote, symmetry transformation. The two other terms, the transformation is canceled using Jacobi identity, right? This transformation was nilpotent, scores to 0. And then we said, because we're interested in gauge invariant state, our physical states will have to satisfy, should be killed by this BRC charge, the generator BRC transformation Q. But not all vectors that are killed by Q are physical. A generic vector that's killed by Q could be decomposed in the following way. A plus Q is some vector. This is a vector that is killed by Q, but it's not Q of something, right? And then this is, of course, Q of something. The point was that the physical states are of this type, right? So the physical states are those states that we should identify, so there is an equivalence relation. We identify states that are related to each other by adding to one of them Q of something. Right? So if we don't want to overcount, we could identify physical states by vectors that are killed under Q, but are not Q of anything. Right? So and that was a role of homology, cohomology. But anyway, that was a BRC symmetry, and I'll leave it at that. Any questions? Say it again.
Why is H not the physical sector?
You have to repeat.
Why is H not the physical sector?
Why is H not the physical sector? Well, okay. Sorry. I have this enormous Hilbert space that includes a lot of unphysical stuff, right? So first, I'm gonna look at this is our schematic, right? A subspace of this Hilbert space, which is killed by Q. All the states that I want to interpret as physical are going to be in this space. Then I notice that any vector, so now this space includes my physical states and other stuff, meaning that it might be overcounting physical states, right? So the overcounting is like this. So every state here, I can write it as some about the notation. A plus Q of eta. Now, this is pure gauge. We argued for that, right? This guy is pure gauge, which means that if I take a vector, right, and shift it by something that's Q of something, I have not, they are the same states, they're the same vectors. So if I want to identify every such state, I define the equivalence class by the set of vectors that are killed by Q, but are not Q of anything. That's just one way of not overcount, right? But that's just, it's just one way of not overcount. They are in one-to-one, the equivalence class is in one-to-one correspondence with such vectors.
But it also has the H naught also includes the close to the
Includes the
close fields and the
oh yeah. So of course, this is one way of not overcounting, but in a different gauge, right? I might be talking, I might still be identifying physical states, right? Sorry, take one of these states, apply a gauge transformation, there will be an orbit. You don't have to pick this state as the physical, as long as within each orbit you pick one state, right? You're okay. Now you could apply a gauge transformation. Under gauge transformation, this vector goes somewhere else, and that's something, right? The point of the BRC symmetry is that it gives you a simple way of identifying the set of physical states and these equivalent classes, right? It's just an elegant way of doing it instead of gauge fixing. Gauge fixing was just painful, right? Any other questions? The connection between homology and gauge theory and cohomology, it goes deep. And if you care for quantum information, it also is related to quantum error correction, topological codes, and such things. Because, for example, the Kitaev code is a D2 gauge theory. So,
Don't talk about gauge theory with continuous groups.
say it again.
Usually talk about gauge theory with continuous groups, but Z2 is discrete, so.
We don't have to. Yeah, in this course, yes. In this course, we were talking about Lie groups, right? But we don't have to. Remember that. How did we end up? How did we? Actually, very good, very good question. So, how did we argue for the emergence of gauge theories with low energies? The way we argued for it, the way we landed on these abelian groups was by we took a lattice. On each side of the lattice, we put a degree of freedom that belonged to a Lie group. The gauge theory, gauge field became the connection, right? Now, I didn't have to pick a Lie group. I could have just picked any group, right? So I could put a qubit. All right. Actually, sorry, I take my words back. It's not literally a qubit, I'll put it on each side. But yeah.
Say spin up, spin and spin, then spin up, spin down. Spin.
No, not quite, but anyway, let me not go into that. All right, good. Non-abelian gauge theory at one loop. So at one loop, the thing that the diagrams want to calculate is the propagator for the gauge boson. That we sort of started the calculation. We went over the calculation of that in the last lecture. So to this propagator at one loop, there are 4 diagrams that contribute to it. The first one is the fermion loop, the calculation of which is identical to the QED calculation. The QED had only this guy. Here's a ghost loop. Here is a gauge loop, gauge field loop, gauge boson loop. And here is also a gauge boson loop by a 4-point vertex. And these 3 are fully non-abelian physics. QED has only this one. Right? So what I'm trying to stress here is that when we calculated this, we saw that, well, of course, if there are a copy, like a NF copies of fermions that run in the loop, this diagram is multiplied by NF. In this calculation, only this term appeared. So I'm telling you in advance that these fermions that run in the loop, they come with a minus sign, if you recall. Keeping track of that minus sign is essential for beta function. So the fact that this is in QED, this was the only diagram, and there's an extra minus sign in front of it, plays a crucial role in the beta function being positive. We'll see that. So it's essential in particular that gauge boson loops are different from fermion loops. we'll comment on the physics of this intuitively in a bit. But sorry, let me just say in words now. This loop, roughly speaking, if we are just using cartoon picture, is telling you about pair creation of electron anti-electron. Right? So it's that we saw, well, okay, I'm jumping. Good. All right. The fermion self-energy is the same calculation as QED, so the same diagram. It's just a bunch of extra indices for the fermion that go further right. The boson fermion interaction, there used to be this diagram. Now there's a brand new diagram. We're going to calculate that. And the counter terms are very similar. Good. Yep. Every time I write this T, it means T of R, the fundamental and fundamental for the fermion. We call this delta 1, delta 2, delta 3 to match the QED rotation. Do you remember what happened with in QED? What there was word identities told us something about the relation between delta 1 and delta 2. They're equal. Exactly. All right. And do you remember the beta function of QED actually? Yeah, but what was the structure of it? There was minus delta 1 plus delta 2 plus delta 3. So basically delta 3 was really the only one that contributed to it. And that delta 3 comes from this diagram. We'll see all of that. I'll review it. That's why the sign of this matters so much for the beta function. All right. So gauge boson self-energy. I'm just reviewing the calculation that we went over very quickly. There are 4 diagrams. 1, 2, 3, 4. Each of them has this form. IG squared over 4 pi squared. It's just fixed by the structure of it. Delta AB. This is fixed by C equal 1 gauge. Right? And word identities. Right? You can't have a mass term. Interval of 0 to 1, d of x, gamma of 2 minus d over 2, delta 2 minus d over 2. So if you recall, okay, good. This is the log term. Every time in any diagram, so hopefully you remember how these came about, right? So there was Feynman parameters, and there was a change of variables, we went to Euclidean space, all of that business, right? But in the diagrams that we were dealing, this is a function of the stuff that runs in the loop, right? Here's what the data of the external legs, right? This is a function of what runs in the loop, right? We're integrating over the momenta here. And it has the following form, m squared minus x times 1 minus xp squared. If it's a massive mode that's running in the loop. If it's a massless mode, for example, gauge boson, it's minus x 1 minus xp squared. So you can redo the calculation, go through it, and see this is precisely a change of the once you do the Feynman parameters and all those tricks. These are the right combinations to introduce. But we saw that precisely, well, I don't want to over-explain. Important here is that there is x going to 1 minus x. This is the log divergent term. Every time you see this combination, that is the log divergent term in MS bar scheme. What is the offensive lambda squared divergent term? What is it proportional to? Gamma of 1 minus d over 2. Right? We saw that term canceled. All right, so there are 4 diagrams. Putting all of these diagrams together, so these 3, we summed it up last time. And so I'm just copying all this stuff out here. Oh, the one last step is that we also, if you recall from QED calculation, we extracted the most divergent term right? And there were divergences that have to do with x going to 0, blah, blah, blah. We dealt with that, and we got extracted terms of this type. So this is the final structure of the coefficient of the divergent term for these 4 diagrams. So this bit is hopefully obvious where it comes from. There is 5/3 C2 of G. This is the adjoint representation. Minus 4/3 NFT of R. This is the fermion representation. So where does this come from? Which of the 4 diagrams is this coming from? The fermion loop. It's pretty clear because there's a coefficient of n of f sitting in front of it. And this is coming from here. Now, this is in C equal 1 gauge. When we did the calculation last time, we saw that there's C dependence, right? So it might be, as is the case here, that these answers are not gauge independent, right? But C equal 1 is a particular case where we split them nicely. All right, so this is expression. This divergence will have to be canceled by delta 3. This counter term. All right, the answer is pretty obvious. So just take this guy, you put it here with the right coefficients, and this is your delta 3. Of course, delta 3 will appear with this renormalization scale because it has to be canceled at the renormalization scale. How does the renormalization scale appear? Like this. Do you recall why it has to be m squared 2 minus d minus over 2? Where does that factor come from? It comes from dimreg. In dimreg, you did not change the propagator, but you changed your integrals to d of x. That changes the dimensionality of the action and everything. To fix that thing, you have to put in front of it scale. What is that scale? That's actually the normalization scale. To what power? 4 minus d, right? And this is what that thing is. Well, d minus 4, d minus 4, yeah. 4 minus the action. In front of the action. Right? So that's the origin. This is the normalization scale. We saw it in various different ways. Good. So if I pick delta 3 like this, it cancels it. What is, by the way, this is supposed to be for non-abelian gauge theory plus matter. What values should I pick so that I get QED? What is C2 of G for QED? What is C2 of G? Let me write this down. What is C2? What is C2 of any R? You guys remember?
Casimir coefficient.
Sorry?
Casimir coefficient.
Exactly. So it's TA of R, or B. Oh, actually, sorry. Yeah, identity, right? Well, yeah, it's this thing. Now, if I pick this to be G, what are my TAs? Yes, but what choices are they? Structure constants. So these are FABCs, right? So what would be the C2 of G for QED? 0. So that term drops out. So right? What is NF for QED? It's 1, right? All right. What is T of R for QED? It's 1. I'm just going to. So this term for QED would be minus 4/3. Okay. All right. So that is the gauge boson propagator at one loop. Now let's move to the fermion self-energy. The diagram is exactly the same as what we had before. This is the thing that's propagating. We pick, it looks like this. Again, there will be C2 of R appearing here, Q slash, you go through this. This is the structure of the divergence. So it's basically C2 of R Q slash. Hopefully you remember what Q slash is. Gamma of 2 minus D over 2. This is a divergent term. And it has to be cancelled by the counter term. This counter term. For that to happen, delta 2 has to be this term. Right? I'm going over this really fast because it's pretty much identical to the calculation of QE. So we can just go back and look it up. By the way, if you didn't take the previous course, I think the lectures are still available. Right? We went through that at the end of last section of part 1 of QFT. Now, all that remains is the vertex at one loop. Yeah, that's the only one. All right. This calculation is very similar to what we did before, right? This is the structure of it. It's a little bit changed now. There's C2 of G appearing here, right? Due to the fact that it's non-abelian gauge theory, right? And then there is this diagram, which is brand new. We calculate this. This is proportional to C2 of G, right? Which means that this diagram is absent in QED because C2 of G is 0, as we just saw. All right. So the sum of these two should be canceled by a counter term. This is the counter term that you obtain. It looks like this. Now, this is delta 1, this is delta 2. If I put C2 of G equals 0, delta 1 is equal to delta 2. But in non-abelian gauge theory, it's no longer true. Right? The adjoint representation contributes to some amount. So the word identities are going to be more elaborate. Right? It's not just going to be delta 1 equal delta 2. What was the form of the word identities? Remember? You can remember. Okay. I won't jump around. All right. Any questions? So by now we've gone through all the diagrams that are divergent and the counter terms. We've absorbed all the counter terms and all the divergence in the counter terms at one loop. Now the question is, so why did we do this calculation? Because we want to calculate the beta function. If you recall, beta function at one loop was very straightforward to calculate if we have delta 1, delta 2, delta 3. Right? We wrote down, I think I did. We wrote down an expression for scalar field theory. We wrote down an expression for QED and any theory that resembled the two in terms of structure, diagrammatics. In QED, to the lowest order, beta of E, electric charge is the coupling, is minus delta of E, right? This is the counter term for the charge, plus half E delta of Z of I. Z of I's are wave function normalizations, right? And in QED became E M del M of minus delta 1 plus delta 2 plus half delta 3. These two guys canceled by word identity, so it's half delta 3. In QED, delta 3 just came from this loop, the fermion loop. The same calculation could be repeated for non-abelian gauge theory in one loop or normalized perturbation theory. The answer is exactly the same. So it's minus delta 1 plus delta 2 plus half delta 3. But all the three terms contribute. So if you want to have fun, you check word identities. What do they imply? All right. Any questions? All right. So let's just plug in the value of delta 1, delta 2, and delta 3 and take derivatives. So if you remember, let me go back here. Delta 1 had this M dependence. Delta 2 had this M dependence. Delta 3 had this M dependence. So the M dependence is pretty trivial. They all come out, right? And you wouldn't be surprised if these terms, just this term and this term are going to be combined to form the beta function. It's just like one line algebra. But the answer looks like this. You put all the diagrams together and you get minus 2g cubed over 4 pi squared. C2 of R plus C2 of G. This is coming from fermions, right? C2 of G minus C2 of R, right? Plus half 5 over 3 C2 of G minus. So this is, yeah. Yeah, okay. Remember that these two terms are absent in QED. This term and this term, they cancel always, right? And then there is minus 2 over 3 NFT of R. You put all of this together and you obtain this answer. 11/3 of C2 of G minus 4 over 3 NF of T of R. Minus G cubed over 2 pi. So now this is what you want to put a lot of energy and focus on, this expression. In an abelian theory, the sign of it is positive. It's pretty obvious. Why? Because there are fermions that run in the loop. The fact that NF says the beta function is proportional to NF, it just means that it's giving you hell. Beta function is positive because there are fermions that run in the loop. What's the meaning of beta function being positive? It means that the charge, electric charge, is smaller at large distances, right? What does that mean? It means that there is charge screening. Quantum effects screen the charge. We're going to go over that, right? But here's this important that what is the quantum effect? Electron positron pair creation, right? That's the only thing. This one loop thing we calculated was fermion, anti-fermion, right? So heuristically, you would say it, you would argue for it this way: QED's beta function is positive, meaning because the charge is screened by fermion, anti-fermion pair creations, right? Generically, this tells you that fermion, anti-fermion pair creation generically screens the charge. But somehow the contribution of other term, the self-interaction of gauge bosons, has an anti-screening effect. It makes the charge stronger at long distances. We're going to see that. Right? Is a principle clear? There's something about, it's not pair creation because it's not, because it's the diagrams, so the diagrams will come, this is pair creation heuristically, as opposed to this thing, and this thing, right? This leads to screening of charge. These are anti-screening. Beta function becomes negative, so these two compete. The signs are pretty obvious. These two compete. If the number of fermions is low enough, this part wins. Anti-screening wins, so you have asymptotic freedom, right? That's so what you a sensible gauge theory will have to have anti-screening. I've made this board up. I'm not sure if it's called anti-screening, but it's the opposite of screening. Yeah.
It should be beta less than 0.
Yes, it's
Sorry?
opposite, right?
Say yeah.
If NF is small enough, beta is less than 0, right?
Oh, there's a sign mistake here. But I think there's no minus outside. No, that's correct. Wait, sorry.
Yeah, because the sign has to be there because when you plug in QD values, then you get what?
Yeah, sorry, if it's small enough, beta function is positive. It's negative, sorry, it's negative, so it's asymptotic free, right? To have asymptotic free, them, you need small number of functions, yeah.
Just in your notes, you get beta GP level zero.
Oh, you're saying that,
Just
sorry,
want to clarify that.
yeah, sorry, that's a typo. Yes, thank you. Good. I wrote beta G larger than zero asymptotic freedom. Okay, the other way around, yeah. So in QED, of course, as I said, this is 0, and then the NF is 1, TR is 1. So what do you get? You get beta of E is E cube over 12 pi squared. That's what we saw. Any questions? So I'm going to try to explain the screening thing heuristically. So let's recall what screening was in QED. The vacuum fluctuation, whoops, leads to the creation of fermion, antifermion, and they will form dipoles. The dipoles will be in this direction, right? Every time you form these dipoles, so the vacuum is dielectric, right? QED's vacuum is dielectric, which means screening, right? So vacuum fluctuation are effective dipoles at length scale 1 over m. Alpha, so if hopefully you recall what alpha was. Do you remember what alpha is? E squared over 4 pi. Yeah. It's a coefficient. Electric charge, sorry, electric potential is minus alpha over r, right? So this is the correction that we found due to the one loop dipole contribution. We did this calculation in the previous part of the course, right? And if you recall, in part 1 of the course, we normalized the coupling so that at distance that was 1 over m, mass of the electron, right? And that's like where the electric charge is 1 over 137, blah blah blah, right? But deep in the UV, it grows. In particular, it has a Landau pole, so this diagram is somewhat misleading. It depends how you interpret. Well, it's not misleading. I can always say it's non-perturbative. I do it non-perturbative. All right, any questions?
We can associate Hawking radiation to the vacuum fluctuation state.
So if you want to talk QED, the analog is a background electric field that's strong enough that electron positron that are produced are going to get ripped apart. So that would be, I mean, it's not, that's nothing, it's not, yeah. The only analog of it in QED, non-gravitational analog of it, is that what you would want to have is called Schrodinger effect. So Schrodinger effect is the phenomenon which is you take QED, you put the vacuum of QED in an electric field that is so strong that intuitively, qualitatively, when the fermion, antifermion, electron, positron are created, they're just going to get ripped apart. They're not going to reannihilate, right? So you're constantly creating these pairs. That would be the analog of it, but you need to pump energy into the system. Anyway, it will have back reaction, all of that, which in the absence of gravity, sort of like you have to put it by hand.
For Hawking radiation, what is the cause of that creation and creation?
Yeah, let's not go in that direction. It's just gravitational field.
I see.
Yeah. Good. All right. So now what we're after is a qualitative origin of asymptotic freedom. So what I'm going to try to argue is that when you have NF copies of these, well, we saw this screening due to the charges right? Due to the fermions, charge fermions is gonna go through the same way. So that minus NF term, sorry, plus NF term in the beta function has the same physics, this polarization, these dipole, dielectric behavior. But now I want to say that the contribution coming from the gauge boson in self-interaction is anti-screening. You want to argue for that. Of course, it's going to be tricky because it's not it's gauge dependent. So I'm just going to qualitatively argue for it by fixing the gauge in an easy gauge in Lorentz gauge and pick an easy group, which is SU2. In SU2, what is FABC? Well, and yeah, so for sorry, SU2 and adjoint, yeah, epsilon is. All right, so what is the equation we're trying to solve? Is d mu, this is the covariant derivative of f mu nu a, is g j nu a, right? In Lorentz gauge and g equal SU2, I'm going to focus on F0IA, which is the non-abelian analog of the electric field. I already said that this beast is not gauge invariant. So that's why I'm gauge fixing in non-abelian case, right? So this is going to be the divergence of the electric field is G, that non-abelian charge, right? Plus G epsilon ABC, this comes from FABC of SU2 and adjoint, A, BI, E, CI. Is this equation clear? So from this equation, I want to argue for anti-screening. Let's pause and stare at this equation for a bit. Good. It is a little bit tricky, so I'll go over it a little bit slowly. If I have an equation like this, where these terms are absent, right? So let's say I have an abelian group, and there are a couple of these gauge fields. So for example, I have U1 tensor, n times, n copies of U1, right? I'm going to have this equation. This equation is the solution of this equation, which gives you the 1 over r squared law, right? This is the Gauss's law. All right, so I'm going to put some rho 1 charge. Rho 1 means E1. This 1 is the gauge index, right? So I put some rho 1 charge, and it's positive sign, so that E1s are outwards facing. All right. Okay. Now let's say I also have an E. So here's my equation for E1, right? So this is the E1. G epsilon 1, 2, 3, A2, E3. Now, okay, good. This is one of the equations. For E3, I have to solve this equation. I didn't put the charge for E. I didn't put rho 3. Which means that effectively, the existence of E1 in some A2 background acts as a negative E3 charge. Right? I did not introduce a rho 3. I just put rho 1. But rho 1 caused E1. And if I happen to be in a setup where I have A2 somewhere, right? A2 fluctuates, right? And the vacuum fluctuates. So if I have A2, effectively, it will act as if I have negative E3 charge. Now, if this is Now, if this is a negative E3 charge, well, okay, I did not. So negative E3 charge means that, let's say you had your row 1 here, and some distance away from it, you had some A2 background. So this is the analog of this picture. Some distance away from it, I have some sort of fluctuating field, right? So some distance away from it, I have some A2. That A2 effectively acts like some flux lines for row 3 that are coming in, negative E3 charge. Okay, I'm missing one. I have not explained this properly, but once you put that, you take that E3 into account, that amounts to, well, actually, no, that's fine. No, it amounts to a decrease in row 1. The angles I'm not drawn actually, the dipole thing. Sorry, let me think for a second. Which step is it that I'm missing? So, of course, E1 will act like negative E3. Now, now negative E3 and some A2, 3 will give me huh. It will act like an increase in row 1, but this step of it I'm being sloppy with. Okay, I'll fix this next time. So I should get plus G2. What am I saying that's incorrect? All right, last step I did not properly explain that why a negative E3 in this equation corresponds to an increase in row 1, but it does.
Epsilon in the second equation, so E3 equals G epsilon 3 to 1. So if we
I added a minus sign for that. That's why there's a minus sign. Yeah, okay, sorry. My bad. All right, I'll go over this next lecture and I'll finish that last step. All right. But what I was trying to say at the last step, which I got confused, is that the effect of the gauge boson is, as it runs in the loops, is anti-screening. And there's a competition between the gauge boson running in the loop and the fermions running in the loop, right? The fermions are trying to screen, the gauge boson is trying to anti-screen. If you have a low number of fermions, then you are going to end up with anti-screening as required by asymptotic freedom. Good? All right. Any questions? Except for the part that I messed up. Okay. So in the remaining 15 minutes, what we're gonna do is we're gonna redo the calculation of beta function using background gauge fields, using effective action. So the reason we want to do this is that first, it's a little bit more elegant. Well, it makes the point of it makes the point that the one loop beta function is fixed by representation theory, very obvious. And also it connects nicely with effective action stories that we're telling in previous parts of the course. So in previous part of the course, if you recall, we for scalar field theory for ON model, we calculate effective action. And the basic idea was that let's just not expand around vacuum. Well, not expand around zero. Let's expand around some classical value. So take the field and write it as a classical field plus quantum fluctuation. And at some point, I wanted to talk about background gauge fields. What happens if we do effective action, if we do the same sort of decomposition for gauge theory? I held back. This is the moment we're coming back to it, right? So I was going back and forth as like whether I should include over there or here. The point of that calculation, well, this calculation is very important in physics for many reasons. But here is a good, the motivation is actually to make the point of, well, it allows you to have another way of calculating the beta function for gauge theory. All right. So the background gauge field method is you take the gauge field, you shift it to some background gauge field, which I'm gonna call a bar. So all the bars mean background, well, it's just a solution to classical equations of motion, plus a mu of a, which is a fluctuating field. So what I'm gonna calculate at the end of the day is the effective action, which is a function of a bar, background field, right? Phi 0 in the case of scalar field, right? It's a function of that, which means that I'm gonna path integrate over the fluctuating field a mu, right? Very good. Do you remember what the procedure was? You take this, you plug it into the action, right? You expand. Then you get a whole bunch of terms that are proportional to this guy. In particular, you will get the action that is just proportional to this guy. It just comes out. Then you're gonna get the terms that are a combination of the two, right? For one loop calculation, we truncated that up to second order A, perform the path integral. Now, in that differential operator, the thing that sits between two A something A will goes a bar, right? If you recall that there was that when we did this for ON model, there was a mass matrix, and the mass matrix depended on phi zeros, right? What did we call them? Sigma, right? So that was a procedure. We got a bunch of, by performing the Gaussian path integral over those guys, we got a bunch of derivatives of the determinants of operators. Log of the determinant was something that we put next to, log of the determinant was the thing that was in the effective action, right? What was the effective action? Log of what I told you. There is the action of this term that comes out, plus log of the determinant, up to the correct powers, right? So that's what the effective action was. And what was the goal of it? The goal of it was that it corrects, it gives you a functional whose variations give you the one pi at one loop. So it's some sort of beefed up action that has in it all the one loop corrections, quantum corrections. So that log determinant better be H bar suppressed, right? It's the H bar corrections, the some H bar expansion. A couple, okay. All right, okay, so let's do that. Before doing that, I'm gonna define something that's convenient, which is covariant derivative with respect to the background gauge field. Let's wait until this sinks. So this is the covariant derivative with respect to background gauge field. And I'm gonna only use the covariant derivative with respect to background gauge field and call that d bar. And keep the rest of it explicit. So if I have the the term for the fermions is going to be psi bar. This psi bar has nothing to do with that. Psi bar d slash bar. This is the covariant derivative for the background gauge field psi plus psi bar gamma mu Ta. Ta is for the fermion, right? Psi A mu A. A mu is a fluctuating field. So there was, this was just a derivative plus this term with A bar, but that term with A bar, I added in here. Right? Okay. F mu nu of A becomes F mu nu bar of A plus D mu bar of A mu plus FABC A mu B A mu C. Right? All I'm doing is, it's just, this is very analogous to what I was doing before. I'm just doing expansion around some background. But the covariant derivative with respect to the background field is the thing that's going to become important. So I can, here's a gauge transformation. Right? In particular, well, I don't know if I'm going to use this actually. I'm not sure if I'm going to use this. Yeah, I was gonna use this, but I didn't. But if you ever need to work with this example, it's convenient. You're gonna find it super convenient to gauge fix in the following way. You gauge fix with respect to what was the gauge fixing? And what's the gauge fixing that we use in this is what was the generalization of the Lorentz gauge that we used for in Fediev-Popov? It was this, right? Yeah. So what we're doing here is that we're doing covariant derivative with respect to background gauge field. All right. So here's the full Lagrangian, where all the covariant derivatives are with respect to background gauge field. I'm also using the normalization where the coupling is 1 over G squared outside of F mu. That's convenient. Is that familiar? Yeah, hopefully. Good. So this is the Lagrangian of Fediev-Popov. Or let's see. I've changed my mind a couple of times here. Here is clear what the gauge fixing is. Right? So this is the gauge fixing I used. I integrate, if Fediev-Popov, I integrate over omega A with a Gaussian weight and I obtain this term. Now, again, this is d mu bar of A mu A, right? And this is the RC gauge, right? I put the C back in. Some point here, I'm going to set C equal 1 and I apologize. But actually, wait a second. All right, let me just go off script. So, very good. I gauge fix this Lagrangian. I still have some residual symmetry. The residual symmetry is corresponds to gauge transformation of the background gauge field. The gauge transformation of the background, because what I'm going to perform is a path integral over the fluctuations, but they still have a residual transformations that should survive. And in particular, I should have the resulting partition function that I get after a path integrate over A's should have this transformation symmetry where this is del bar, right? This is the gauge transformation of the background gauge field. Now the point is, this symmetry, this background symmetry is extremely powerful in calculations. It's a very, very powerful tool. Right? Good. All right, so what we would like to do is to compute the effective action at one loop. What we're gonna do is that we're gonna take the action. I'm gonna pick c equal 1, linearize, and keep only terms that are quadratic in fluctuating field and perform the path integral. Here is a list of all the part of the Lagrangian, which is only a squared terms. This is what it looks like. The curvature, the curvature of the background gauge field appears here, right? I can do integration by parts to make it look like this. Does this look familiar? A term of this type. This is like the inverse propagator, right? Roughly speaking. If these were usual derivatives, they would give you q mu q nu, right? And it would look like q squared eta mu nu minus q mu q nu, right? Except that I picked c equal 1, so these two terms cancel, right? Because if you remember, the term in arc C gauge had a coefficient of 1 minus c outside of q mu q nu. Now, in non-abelian gauge theory, this commutator is actually f mu nu bar. So I can further simplify, and I obtain this simple Lagrangian. So it's basically the covariant derivative of the background gauge field squared, eta mu nu, minus 2 FABC, the covariant, the curvature of the background gauge field that sits in the middle. All right, let's stare at this for a couple of minutes. Ooh, I'm running behind. Okay, I'll finish it, but I'll do it quickly, and then next lecture I'll go over it a little slowly. Right? So these are the fields that are second order in A mu. Right? In principle, I have to do this for psi field as well and perform the path integral for all of these guys. Right? So in anticipation, and for the gauge field as well. In anticipation for that, I'm gonna massage this expression so that I can write something that's a little bit more elegant. Turns out that if you introduce this J rho sigma operator, which is this is just the generator of Lorentz transformation for a 4 vector. Go back to part 1 of the course. This is the generator of Lorentz transformation on 4 vectors. I can repackage this expression in this form, and this is TB of GAC, which is FABC. So that's might sound fancy, but that's what it is. And this just F bar B mu nu. I just changed it this way, and these contractions make sure it's back to mu. Right? So why do I write it this way? Because the contribution of other terms I can write this way as well. Let's look at the fermion. So in fermion, we're dealing with this term. When we expand it, we're gonna have minus d bar squared. Sorry, I'm gonna take the slash and square it. I'm gonna need to calculate the determinant of the I d slash. How do I calculate that? The trick that we use in quantum field theory is that we square it, we calculate the determinant of the square and take half, take the power of half, right? So we're gonna square this guy. So you get minus d bar squared minus half, a similar expression, but look at the analogy. Here I had TBGAC, here I get TBR, right? It's just the generator of the Lie algebra, element. And J rho sigma is just replaced by Lorentz generator for spin half fields. The rest of the expression is identical. So I define a covariant background field, the Lambertian, which is minus del bar 2, d bar 2, plus 2 times half f bar j rho sigma tbr. This is the Lorentz generator for spin j, and this is in representation r. This differential operator I define is only a function of the background curvature, gauge field, right? And from the fluctuating field, the only thing it cares about is J and R, right? It's just representation. Group representation, space time spin, right? Now, what is the effective action? E to the power of I, E bar of A, of course, it's a function of the background gauge field, is you have to path integral over the fluctuating field of the whole thing. I'm going to get the answer. There will be a piece that's just the action, e to the power of I integral of the action of the background gauge field that comes out. The rest of it is going to be a bunch of determinants. There will be a determinant associated with the fermions to the power of, I think this is capital N in my notation, and F over half. Why is a half?
Because it's that delta one is getting squared.
Yeah, it's ID slash, when I squared it, I have to put the half back. Why is it positive? Because it's fermions, right? Delta of G, this is a gauge boson, minus half, right? A spin 1, spin half, and what is this one? That's a ghost, right? It transforms in the adjoint representation is a scalar, Lorentz scalar, right? And it's just plus 1, yeah, because it's ghost. It's anti-commuting. Thank you. All right. Okay, I will not have time to finish it. So let me just summarize. Let me just say where I was going with this. No, actually, I'm going to summarize. So today what we did was we calculated the beta function and non-abelian gauge theory plus matter plus coupled to matter. And we saw that the expression had a negative term coming from number of fermions that were running in loops. And that has a screening effect. But the self-interaction of the gauge boson had an anti-screening effect, which meant that if NF is small enough, the anti-screening term wins. So in long distances, the charge is enhanced, therefore you have asymptotic freedom. Good? That was the message. Then I started talking about the effective action for some background gauge field. And we went through the calculation. The calculation, we got it up to this point that effective action, of course, there will be classical part to it, which is just the action of the background gauge field, right? Times these determinants. Now, is it clear from here that this is going to be invariant under background gauge transformations? Anyway, that's for you guys to think about. But this is the effective action that we ended up with. So in the next lecture, we're gonna massage this effective action using Wilsonian approach to RG to rederive beta function and see in another way that the beta function of Yang-Mills ends up being positive. The theory is well defined. It exists as an interacting theory in 4 dimensions if NF is small. Right? Also, from this, you might learn something important. The message from here is very important. If you recall, when I was talking earlier about these Wilson-Fisher fixed points, right? The beta functions that I flashed a couple of times had a structure that was very similar. There was a bunch of coefficients multiplied by the number of fields, some group theory, but it's just like a bunch of summation and subtractions, right? So because the one loop beta function in this formal, in this type of models is it's just fixed by representation theory. It's not hard to cook up setups for the bit to tune. Well, you could cook up models where the beta function at one loop vanishes and look for fixed points. Right? All right. Okay, I'm not gonna go through any of this. I'll stop here. Are there any questions? Sorry, I went over time.